Hi everyone, I'm back after an exciting week in California. I figured it's good time to update all of you on what my view is on the state of the world of self-driving and autonomy. So obviously it's a very fast-moving world that keeps changing basically on a monthly basis. And I think it's definitely clear that the whole industry has gone into some sort of hyperdrive mode in the last 2 years. Largely kind of triggered by China's rapid ascent and huge push to innovate in the space of self-driving cars. So for context, and before we dive in, I'm Daniel. I'm co-founder and CEO of Cognic. And Cognic helps humans train machines that move. So obviously for us, it's extremely relevant to understand what the frontier is of how machines are trained, so that we can be as helpful as possible to our customers. And a major part of our premise as a company is that everything that moves is becoming autonomous right now. So it was very inspiring to see in San Francisco how ubiquitous the Waymo self-driving cars are by now. They are basically everywhere. And in 2025, somewhere around this time, they are at 13 million annualized driverless paid trips. That's a huge number. In parallel to that, there's a rapid rollout of increasingly capable self-driving functionality on the passenger car side. I think BYD is perhaps the most exciting company, considering their enormous fleet. So they plan in 2026 to roll out their version of an L2 Plus system to more than 4 million cars for free. And the strategy behind this is BYD has understood that the race for autonomy is actually a data race. So they're trying their best to build the largest possible data set out there. And then on the kind of nascent side of things, robotics is finally becoming a thing. So when we founded Cognic 7 years ago, I was talking about robo-taxis and everyone thought I was kind of crazy. I think the progress I'm seeing right now gives me reason to believe that where robotics is today in 7 years is it's gonna move into the left side of this frame. So robo-taxis are now finally becoming a commercially viable business. And I think robots are on the brink of a similar exciting transformation. So basically, today in 2025, most cars are still dumb as toasters. And what do I mean by that? Well, if we look here in the 2025 autonomy penetration level, it's at around 37%. So basically 2/3 of all new cars sold are either L0 or L1 today. So L0 means drive yourself, no assistant whatsoever. L1 means that you at least get adaptive cruise control. So that means you can take your feet off the pedals. This is, not exactly science fiction. It's been around for a long time. If you're on the highway, you set the speed. You can still you need to still hold on to the steering wheel, but you can relax a bit and take a step back. And then in the last 5 years, sort of level 2 has become an increasingly common thing. Still relatively rare, but it's becoming much, much more common now, especially in premium new cars. So Tesla's Autopilot or FSD, full self-driving, I guess is the latest version of that name, is an example of such a system. So in theory, it gives you the ability to take your hands off the steering wheel and let the car control steering wheel actions for a while under very specific constraints. So a concept you need to know about here is operational design domain. That's specifying where a system works. And the dynamic driving task is what the system is able to do. So that's where we're at roughly today. And the challenge now is to transition from an L2 system to an L3 system. So L3 is basically L2, but you can take your attention away and have the car be liable for potential accidents. So basically the big shift is that in L3, the OEM, the car maker, the original equipment manufacturer, basically says, we are so confident this system works under the constraints we have declared that we are prepared to take responsibility for whatever happens. And that's still incredibly rare. So Tesla, for example, refuses to assume liability for its system. And that's, I think, quite telling. Drive Pilot, which is a product by Mercedes, was, I think, the first one to actually offer this functionality. Honda also had a very early version, but volumes are very, very low for these products. And then in the higher tier, there's the Waymo Robotaxi, which is basically you're a passenger. There's some discussion about sort of how to make the distinction between L4 and L5. Doesn't really matter. The point is that like there's some clear levels here where L2, you're very much in charge yourself. You are liable for what the car does. L3, you can take your hands and eyes off the steering wheel and the OEM will pay the penalties if there's an accident. I mean, it's your risk because they can't revive you if you die, but at least the liability part is there. And then for L4, you get in the back seat and the car drives you somewhere. So for robotaxis, Waymo is obviously the dominant player, with Tesla now opening up some very limited functionality in Austin. And that's what we're going to cover in this presentation, is kind of where is that race right now and where might it be heading in the next months and years. So obviously, the history of self-driving has been a kind of summers and winters phenomenon where the origin of this wave of self-driving, I would argue, is around the time of the DARPA Grand Challenges. So that's around early 2000s. The Google Waymo Chauffeur Project X, whatever you want to call it, that project came about somewhere between 2005 and 2010, depending on where you start the clock. And that means that it's taken 15, almost 20 years to go from these early, very impressive prototypes to something that is now commercially viable. So making a demo for a self-driving car is wildly different from delivering an actual product. And this is perhaps one of the most confusing aspects for technologists, because in many domains, getting 80% of the way to a working product is the big job. If you can get something 80% good for a customer, that's maybe enough for a long time. In self-driving, it's a very different game. You actually need to get to like 99.999 or whatever, like a super high reliability for it to be viable at all. And it's sort of, you either make it work or you go bust. There's like very little middle ground. So as a result, investors and others have been first excited and then depressed and excited and depressed. I think now we're back in excited, as indicated by Mark Andreessen saying self-driving cars really do work. And I think that statement is largely informed by the results that Waymo have demonstrated in San Francisco. So that's obviously very exciting that we're now at a point where investor sentiment is back as a positive. So two very different philosophies are currently competing in this space. And they are best illustrated by this image from Austin. So on the left is a Waymo. It's an incredibly sophisticated car. It's very expensive. It has some state-of-the-art sensors, and actually a lot of them. There are tons of cameras, very high resolution, long-range LiDARs, radars that can basically see through objects. It's a beast. On the right-hand side here, you have a Tesla. The Tesla has originally 8 cameras. I think it's down to 7 now. It's basically video-based, and the cameras aren't even that high resolution. So you essentially have this massive beast of a machine with tons of sensors and this very kind of budget version. And the reason these two cars exist in parallel with such radically different philosophies behind them is the tension between safety and control on the one hand. So Waymo comes from a traditional safety engineering culture, sort of informed by what's going on in aerospace and traditional automotive. You want to have all these types of certifications and guarantees on the functionality and the behavior of the system. So you have to have a very strong argument for why the system will behave in a safe way to be certified traditionally. On the right-hand side is a bet on scaling laws, essentially. So Tesla is an AI maximalist company, I suppose. And my understanding and my kind of take, and obviously from an outsider's perspective here, but is that they are betting that scaling laws will hold and that budget sensors won't be a constraint, and you maybe don't need to close the safety case. So we're going to get back to what that means, but this is the interesting and challenging battle of philosophies that is going on in the world right now. Before then, I wanted to kind of make a kind of perhaps a surprising jump here and start from something that could explain these two companies and how they came about. So I started my career as a machine learning guy in natural language processing. And it happens to be that the evolution of natural language processing is quite informing, or I think is quite informative for what the world of autonomy is going through. So when I started in natural language processing, it was still popular to do these very detailed data annotations to train models. So researchers believed that in order to generate and understand language, you needed things like part of speech tags, named entity recognition, co-reference resolution. These are low-level features of language that humans don't actually explicitly think about, but that we probably implicitly use to understand and communicate. The big if here is to what extent this is necessary. In the absence of today's kind of end-to-end trained, deep learning-based natural language processing models, NLP, or today just called language models or large language models, LLMs, this was the predominant paradigm. This is very cumbersome to create, so you need very careful data annotation. It requires tons and tons of effort, and it became a bottleneck. So a similar kind of paradigm has been in existence in autonomy for quite some time. In the supervised paradigm of autonomy or computer vision, you would create these bounding boxes, and there are tons of different kinds of geometries. It's not just boxes, it's lane markings, it's connections between things. And this then would be used to train, for example, convolutional neural nets that could take a camera feed, detect all the different objects. This would be a fundamental part of the perception part of an autonomous vehicle. So the traditional stack for autonomy was divided into perception, prediction, planning. So you would tons of data, collect data for training perception. You would manually label it so that you could supervise the system based on that kind of data set. You would then train prediction models to understand possible paths for different objects. And then you would finally plan your path. So this would be the traditional supervised approach to training these kinds of systems. Obviously, since then, natural language processing has quickly evolved, and the dominant paradigm now is attention-based transformers. So basically, you have done away with all these explicitly labeled parts of speech and co-reference resolution things, and instead you do autoregressive token prediction. So that's a lot of fancy words for just saying predict the next word based on whatever words you've seen so far. And you do this token by token by token, and you take into account what tokens you've seen before. So I've made previous videos explaining in more detail how transformers work and how attention works. For this context, let's just say that's the dominant paradigm for LLMs today. The thing is, though, that in order for these LLMs to work, you need absolutely mind-blowing amounts of data. Latest generation of LLMs are trained on trillions of tokens. So basically, these types of models benefited hugely from having an entire internet of data that you could download. And AI companies have gone out of their way to capture all data that they can possibly get their hands on, both, legal and illegal. I think it's like the worst kept secret of the Bay Area is that these AI labs are basically stealing whatever text they can get their hands on. But they're running out of such text. And even then, I'm not sure this shift in technology would have been possible without the enormous amount of text available online. And the question is, now that we're kind of running out of text, what's going to happen to improvements? Because there's only so much you can do by scaling up compute if you don't have enough data to train on, because these systems rely on signal. I mean, saying that LLMs are unsupervised, I think is kind of bullshit, because you needed all of the internet to train them. Like, humans have had to write enormous amounts of text about how words belong together in order to train these models. And these data sets have grown at an enormous rate. So we're now at 10 to the power of 30 tokens in the latest generation of data sets, as reported by Epoch AI in May of this year. And they've been growing at 260% per year for the last couple of years. So what happens when this data set size plateaus, or when we've sort of run out of the internet? Well, as a result, there's an enormous demand for human supervision again, human feedback. But it's not on the form of, part of speech tags. It's writing text. So basically, explaining how to solve a problem with language is increasingly becoming a huge in-demand thing for the AI industry. So some call these eval sets, some call them training data sets, whatever you call them. I think the latest frontier for AI research is basically having humans carefully write down how to solve a wide variety of tasks, all the way from lawyers to medical doctors. There are now people employed to just create data sets. And obviously, Cognic has been riding on this understanding of the world with the explicit focus on autonomy. So what is going on with data sets in autonomy is a pretty relevant question. And how is the nature of data annotation changing as autonomy is evolving? That's part of what we're going to cover in this talk, but it will sort of be mixed in with the state of autonomy as a domain. And this is incredibly expensive, right? So the big six in the US are now spending, more than $250 billion a year on CapEx. And the global data generation is now north of 150 zettabytes. So we're just cranking out data like crazy. The big AI labs and the big six are spending enormous amounts on building out compute and creating and fine-tuning these models and accumulating massive data sets. So this is both good and bad, right? So an L2 plus system in autonomy can generate up to 4 terabytes of data per day. Our latest forecast is around 2030, there will be some 200 million L2 plus cars in circulation. So if you just do the math on that, that's like hundreds of exabytes of data per day. And maybe that's too high of a number to be useful. Who knows what the evolution of storage and compute is going to be in the next 5 years. But even if we throw away, 99.9% of this, we're going to be overflowing with data. So the real question is, how much of that data is useful and how much of that data can we afford to use when training? So that comes down to how much of this data can you trust? So Ilya Sutskever, who started OpenAI, he gave a talk a few months ago, and his main concern with the current paradigm is that we're running out of data. Data is not growing. Data with good signal is not growing. We are getting better hardware. We are getting better algorithms. Scaling up clusters is an industrial problem. I mean, all it takes is money, basically. Obviously, a fair amount of skill too, but it's sort of engineering as opposed to science. But there's a much higher barrier to solving the lack of data set growth, right? It's much harder to solve the slowdown in dataset growth than it is to just build out larger clusters of GPUs. And as much as simulators would be nice as a part of the solution, we don't have the matrix as a Docker container today, right? Like, that's still just a movie. And the world is so nuanced and full of subtle details that coding those into simulators will be a very expensive endeavor. And it's going to be the same kind of long tail problem as reality presents. So there's obviously tons of value in simulators, but it is not the solution to end all problems in this domain. And finally, even if we do build great simulators, there's only so much that can be understood from physics. I mean, if you want to understand humans and interact with humans, you have to interact with humans. And that's a constantly shifting distribution of preferences and opinions. So it needs to be continuously updated. So what this means from my perspective is that there's this trade-off right now. So on the one hand, we want as much data as possible. But if it's low quality, you're going to be paying for it in terms of huge amounts of GPU and storage. So let's say that you are collecting clips from a fleet of cars, and these clips show people driving. How do you know which clips are relevant to include when training your model? One option is you say, I don't care, I'll just collect as many as I can and train on all of them. What is the consequence of that? Well, first of all, you're going to be getting an enormous amount of clips. And that will be both expensive to train on. It will result in larger and larger models. And you need to store all of that data, which is incredibly expensive. The benefit is maybe higher performance, assuming the driving that is happening in these clips is good. Because who knows, right? If you have millions of drivers out there driving your cars, like BYD plans to have next year, not all of those clips are going to be exactly desirable from a product perspective. On the other hand, if you focus too much on data quality, you will suffer from lack of coverage. So you want to find all these edge cases and all these important events and all these rare events in order to deliver the customer experience customers expect. So if you want to deliver, navigation on autopilot, parking lot to parking lot, which is increasingly what customers in China expect. So this, by the way, just to kind of interject here, consumer behavior across the world is currently evolving in very different ways. So customers in Europe are generally more skeptical. To be honest, so are customers in America, even though there are pockets of more progressive customers in both geographies. China is just a different universe. Like Chinese car consumers expect way more autonomy in their cars than anywhere else in the world. And vendors in China, OEMs and their ecosystem also deliver way more autonomy. The question mark is the type of functionality they get safe, and are they actually informed as consumers about the safety concerns? And we have no idea how many accidents actually happen. So kind of going back to what is the customer promise, I think the goal is obviously to get as much data as possible, but you have to balance the trade-off between quality and volume because of compute constraints, essentially. If you are compute unconstrained, which you could kind of argue Tesla maybe is, then including more clips could be part of the solution. But it's very much sort of a hypothetical situation that we haven't really fully understood yet. So scaling laws become a matter of incredible interest here, right? What happens as volumes of data increase and as we throw more compute at it? So fortunately, people have started studying this in great detail. So Waymo released just a couple of weeks ago a technical report on the scaling laws of motion forecasting and planning. And basically, they are concluding that more data and more compute makes models better. That's not perhaps a huge surprise, but it's good that it's formally studied in a verifiable way. They also find that model sizes, in order to absorb all the information in the data, need to grow about 1.5x faster than data sets. So basically, you need to get as much data as possible to cover all the rare and interesting things. And as a result, models need to grow actually at an even faster rate. And as a foundation for these kinds of studies, the emerging kind of end-to-end paradigm is obviously the foundation. So in traditional self-driving, you had this perception, prediction, planning setup. The Waymo paper is based on an architecture called Motion LM, which is basically you take some amount of explicit information about the environment, like traffic light and traffic signs, or traffic light signals and the information they convey. You have a so-called road graph that gives you information about lanes and curbs and their connection to each other. And then some history of the car and the other cars in the environment. Those are then projected into an embedded, a latent space that can be consumed by a scene encoder. So basically, you want to turn your understanding of the environment into a vector, an embedding, that you then use when you try and predict or forecast the most appropriate actions. So the decoder in the end outputs basically turn signals and acceleration and deceleration. So these would be the kinds of things showed on the right here. And the vocabulary in this case, using the terminology from language models, is basically these little arrows. So you can think of it as a lot of agents interacting in an environment, and your prediction task is to output a sequence of these little arrows, the same way that language models output tokens, but the tokens just indicate how to turn. So for every timestamp in your modeling environment, I mean, the frequency of this depends on the setup, I suppose. You want to create these trajectories, basically. And since these are non-deterministic, you can get different trajectories for each time you sample. So basically, there's an ensemble approach here where you generate tons of different trajectories for each object, and you cluster and group those to find the most likely trajectories, and you do this continuously as you drive. So basically, the assumption here is that the more driving you observe, the more informed these language models, I'm using sort of apostrophes here, will understand how to predict the next token. So if this paradigm works, it should scale in a similar way as language model scales, maybe. Another type of this kind of scaling law is generative world models. So basically, you can not just predict what actions a car should take, but in fact predict the entire visual scenery around you. So Wave is a pioneer in this space. They've published a lot about their Gaia world models. So these models use camera inputs to basically generate driving scenarios from diverse locations. So that includes the entire visual impression, and since you know what you're generating, you also kind of get ground truth for free in these kinds of generators. What's worth noting, though, is that this requires a lot of data and compute. So they've carefully curated a large, diverse set of driving clips, and the model they've published uses 25 million 2-second clips collected from over a long time period in a lot of different countries. So this is another example of a kind of scaling law where on the one hand you have sort of the language model approach to predict actions. On the other hand, you have the more kind of comprehensive problem of just generating reality to use as a driving simulator and as a way to inform your driving policy. Both these approaches obviously benefit tremendously from more data. Another angle here that is under intense debate is to map or not to map. So traditionally, companies like Waymo have relied heavily on detailed HD maps. So you see an example of a lot of the types of attributes you might need in order to drive in the traditional paradigm. Lately, a map light or mapless approach is of growing interest, just simply for scalability reasons. So pioneers in this area, like Tesla, they are, instead of relying on these detailed HD maps, doing online road structure inference. So you do kind of bird's eye view synthesis of your sensors, and you can do lane detection and segmentation in these bird's eye views. And you can train these using HD maps or maps, but then run them at inference time without the maps. And to localize yourself in the map, you can do structure from motion, odometry, visual place recognition. There's all these different techniques to position yourself. And obviously, again, dynamic traffic light association is a tricky problem, where if a traffic light shows red, yellow, green, how do you know if it applies to you in the position you are in? HD maps typically have such information available, or you can collect it and curate it. That's part of why ensuring performance in a certain operational design domain can be much easier than providing general driving capabilities in an arbitrary location. Obviously, from a scalability standpoint, if you solve these tasks dynamically from data, you can move into any area. The counter argument would be that in the learning part of that expansion, you're going to have some serious performance problems. So I think we're gradually coming up on what I believe to be the situation with Waymo versus Tesla. And if we dive a little bit deeper into Tesla, what we know is, at least from publications, is that a few years ago, they called it HydraNet. Who knows if that's... I don't have insight into the absolute latest of Tesla on the internals, but let's assume this is roughly how they do it. There's some sort of uniform video transformer system that takes the 7 cameras they have, converts that into a representation in a global coordinate system, and it's not modular CNNs, it's just one giant network as far as we know. It does not use HD maps. It does not use explicit indication of traffic light states and relevancy to where you are, etc. Instead, this HydraNet, so Hydra is obviously a multi-headed snake, and neural networks can have prediction heads. So this network has multiple prediction heads, hence HydraNet. And these different prediction heads do things like 3D occupancy estimation, lane boundary, lane topology, traffic light state. The list goes on. You can read for yourself. And there's no LiDAR. This basically is a massive bet that scaling laws hold to such a degree that you can deliver safe, high-performing self-driving by just jamming as much data as possible into a network like this. That's the bet. Neither more nor less. And it's not magic. Like, I think the more I travel to California and talk to people, and the more insight I get into Tesla and other companies, is that Tesla is not a science company, right? Like, they are rarely inventing things. That might not be the perception people have from the outside, but like Tesla, it does not have a strong kind of systems and science culture. It is an engineering dominated company that is largely excellent at scaling things up. So when you have something that works, Tesla is extraordinarily good at doing that at a low cost, at a large scale. So this is, I think, the battle of philosophies between Waymo and Tesla, where the question here is going to be, will regulators and the public allow a brute force data-driven approach to autonomy with all the different error modes that presents? Or will the public and regulators favor a Waymo approach that is much more safety-oriented? Let's go back and just kind of speed through everything we've said so far to fully enforce what these different philosophies are. So we have Waymo on the one hand, Tesla on the other hand. We have the kind of transition from these explicitly informed models, completely analogous to what the transformation has been of natural language processing, where in the traditional supervised paradigm, you have these very explicit representations. We then have moved into a transformer, kind of end-to-end, attention is all you need kind of paradigm, where you want to learn as much as possible without explicit intermediary representations. The consequence is that you need an enormous amount of data. So what you win in terms of performance and nuance and ability to replicate human-like behavior, you pay for in the enormous amount of data you need and the corresponding increase in compute requirements. So you need to spend tons of money, gather tons of data. But if you do, and you also make sure that you clean this data in as good a way as possible, what you get is a combination of quality and volume that leads to tremendous performance. So the E2E paradigm, the end-to-end paradigm, I think from first principle is going to deliver higher performance, assuming you can afford the combination of data collection and curation and compute required to cover enough of your operational design domain. And Waymo themselves have basically confirmed this in their scaling laws of motion forecasting and planning report recently. And it intuitively seems reasonable that if you use a kind of encoder-decoder paradigm and you can project the different environment things into an embedding space, a latent space, the kind of ideas that are true for language models should probably also be true for multi-agent dynamic driving. You can go into all these details. I recommend reading these papers. You can even go as far as to generate entire world models from this kind of thinking. You just need enough diverse data, 25 million 2-second clips in this case. This could lead to the ability to get rid of the dependency on HD maps, which is a big part of how Waymo, for example, solves the problem. If you can do online road structuring, etc., that's way more scalable. And that's essentially the idea that underpins Tesla's HydraNet. It's a single giant transformer-based architecture that takes video as input and outputs all these different intermediaries like 3D occupancy, lane boundaries, traffic light states, etc., etc. The potential counter-argument is that it seems inevitable that during the rollout of such a system, people are going to die. And that's what we're seeing in China. It's very, very hard to get a clear understanding of what's going on in China because of censorship and regulation. But that kind of brings us back to where we started, right? So on the one hand, you have this more traditional, more safety-oriented approach where you have way higher sensor capacity, more overpowered sensors, more carefully designed underlying systems, more, if you will, explainable and interpretable systems. Those give you a better foundation to close the safety case. On the other hand, you have the Tesla approach, which is essentially a bet on scaling laws. And I think the long-term performance of a camera-based system trained on ginormous amounts of data could very well be both better and sufficient. On the other hand, that system is likely to make a lot of unexplained errors in the meantime, and we won't really know why they happened and how to fix them exactly. And either way, both approaches are going to need stupendous amounts of data. So much that you can't include all the data collected by cars into your training anytime soon. So you need to find out smart ways to select which clips are suitable for inclusion. So from Cognix's perspective, just going back to us, I think that the value of quality data remains. It just grows, actually, as you transition to a more end-to-end oriented approach. But the nature of the tasks that we do, the kinds of human feedback we provide, is changing. It's less so about the bounding boxes and the lane markings as such, even though they still need those for evaluation or evals or validation. So the car industry traditionally called it validation. The AI community has mostly moved to the term evals or evaluations. Either way, explicit intermediate representations are necessary to measure performance, even if they may not be necessary to train performance in the first place. Instead, I think the types of human feedback we need to provide is around reasoning, understanding scenarios, and doing quote-unquote weak perception on huge amounts of clips. So you can't apply too expensive of an AI model on all that data. You also can't do a full-blown perception inference on all your stored data, you need to have the lowest cost possible information that you can get from a clip in order to triage it for inclusion. And you need to apply human judgment at the most high leverage parts of that funnel. So tons and tons of clips are coming in. You need to throw them away as much as you can. Some of that is going to be automated. Some of it is going to require a bit of human inspection. And even if we reduce the amount of human effort tremendously in the next few years, the data explosion that we're about to see offsets most of that. And we get, in fact, a net increase in demand for human feedback. So my conclusion is that human feedback is necessary to turn these massive sets of recordings into trusted data sets. It's a challenge because it's both too expensive, it's too difficult to scale up, and it's too slow. So as a result, that's why Cognic has sort of invested and continues to invest in the world's most productive annotation platform for autonomy data. We think that by providing super productive annotation tools to basically take these human feedback instances and handle them at the highest possible throughput. So the faster, cheaper, and more reliable we can make that, the less of a bottleneck this becomes to develop autonomy. So ideally, my customers can put every instance that they're not sure about on a queue, and Cognic just consumes that queue, sending you back high-quality human feedback on whether to include or not include, how to interpret this scene, how to understand what's in it, be it on a bounding box level or on a general scene description level. That sort of information, together with powerful integration of auto labeling, that's how we make this scalable so that it covers the entire world. So only a tiny, tiny fraction of the world is still covered by data collection. And we're going to need exabytes of data to get this globally rolled out in the next few years. So I'm very excited about the future. I'm very excited about the kind of work it's doing and how that contributes to this. I think it's hard to know which of these two philosophies will win. More importantly, because predicting the future is maybe not so hard if you're not forced to specify when exactly, right? So I think Tesla's approach, I mean, I bash on it to some extent because I think it's a bit reckless. But I think from first principle, I gotta admit, it looks more scalable and it looks more performant eventually, probably. The challenge is that on the way there, it's very, very hard, if not impossible, to close the safety case. So the real question is, are we prepared to allow experimentation in public the way Tesla is doing, where each car is essentially a guinea pig in a giant experiment of data collection? If we're fine with that and all the accidents and fatalities that likely will lead to, I think the approach eventually is going to be rather high performing. But to me, that's not a great way to think about human life, basically. But that's a matter for regulators to figure out. I mean, public opinion will matter, and the way the public feels about this will, I think, determine how regulators act. If, in fact, Tesla scales up their robotaxi experiment outside of Austin in the next year, and we start seeing large amounts of accidents and fatalities, it's highly likely, if not almost certain, that the regulators will react. So I would feel much safer with the Tesla, I would feel much safer with the Waymo approach to things, just because I know the amount of safety engineering and careful design that's gone into those cars. But of course, there's no denying the fact that they are expensive machines. It's a much more difficult to scale up deployment. And still, they are doubling their number of paid driverless rides every year. So it's not like it's impossible to scale up. It's just more honest to acknowledge the fact that it is a more expensive platform to scale. So this is my attempt to provide a balanced and nuanced perspective on this. I think from my perspective, there's no denying the fact that end-to-end is definitely the paradigm that is going to dominate in the next 5 years. I think we should expect to see even chain of thought reasoning go on in real time in cars. I anecdotally heard that a Chinese OEM is looking for chips with 5,000 tops, which may not mean much to most of you, but to some, you'll understand that's a lot. It's not long ago you had maybe 100 tops on an in-car chip. Latest generation of NVIDIA, etc., is maybe 2,500. Chinese companies are looking for 5,000. And part of that is you want to run as much reasoning and have as much token capacity as possible in real time on your car. So whatever happens, it's clear that scaling up data and compute will lead to exciting new results. And probably a good strategy to develop autonomous driving is to deploy to as many cars as you can, collect as much data as you can, and then be as careful and precise as possible about selecting that data to minimize the cost of compute and get the highest quality signal as possible. And if you can do those things while also closing the safety case, you will have a pretty good product, I think. So I'm very optimistic about self-driving in general. I think that in the next 10 years, we're going to see an extremely impactful shift from you owning a car to being able to summon a car when you need it. Sounds like science fiction, but it's increasingly true in some parts of the world. And as the old saying goes, the future is already here. It's just unevenly distributed. That's it for this. Thank you so much for your attention.